Hello, welcome back. Today we're going to be discussing the policy-based routing feature known as PBR. My name's Lee Wooderson. I'm actually a CCIE in routing and switching. If you've got any questions, please feel free to either email me or use the comment section below, and I'll always try and answer your questions. So in this video, we're going to go over what PBR is and why you would actually want to use this feature. We will then go over the configuration and talk about how it all pieces together. And at the end we will finish with a short demonstration. So what is PBR? Now essentially PBR allows you to override the routing table and in turn override the forwarding table. You may be running OSPF and it's calculated that link A is the shortest path, but you may want to create an exception to this and for a specific set of criteria send traffic via link B. PBR would give you the flexibility to do that. Now, as we know, normal routing logic uses the destination IP address and the longest match routing principle to make the final forwarding decision. Now, PBR lets us forward based on further criteria such as source address, port, protocol, incoming interface, and we could even match on things like the size or length of the IP packet. Now, you may have a scenario where you want to route web traffic one way and SFTP another, or more typically you may have a scenario where you want to route voice traffic down a more expensive lower latency link and default all other traffic via a cheaper higher latency link. PBR has other uses as well. You could use it to route traffic based on certain criteria, but then additionally set a particular IP precedence or DSCP value for QoS. It can be used for traffic leaking between the global table and a VRF. It can be used to just drop traffic by setting the outgoing interface to be null zero. Now, I'm not going to go into all the details and all the different use cases, but I recommend you read through the documentation and I will show you where that's documented before we do the demonstration. Now, one thing we need to be aware of is that the match criteria and PBR features available to you are going to be highly dependent on the platform and software version being used. So I recommend you check the release notes and configuration guides before implementation. Another big caveat we need to be aware of is that most platforms run PBR in software, which means it's going to be process switched and punted to the CPU. So I recommend only using PBR if you truly need to and be as specific as possible in your match criteria. So PBR can actually be applied in two different ways. The first and most common way is to apply the route map inbound at the interface level. The second and less common way is to apply it globally, which is used to policy route traffic sourced from the router itself. One use case for this would be if you wanted management traffic such as Telnet or SSH to always go out a particular interface. You must be very careful with this though, as you can easily bring down the control plane through misconfiguration. The last thing you want to do is policy route your ERGRP or OSPF hello traffic out of the wrong interface, which obviously will bring down the neighbours. Again, like I said in the previous slide, it's best to be as specific as possible in your match criteria. When it comes to the configuration, it's actually fairly straightforward. We first create a route map and give it a name. We then use a permit if we want to policy route the traffic, or we use a deny if we want to ignore PBR and have normal forwarding occur. That actually makes sense, as the implicit deny at the end of the route map means anything that wasn't matched in a permit statement will not be policy routed. So we now need to specify the match criteria. In these examples we are matching on standard access list 10, but you can also use extended access lists, allowing you to match on both source and destination. You can also match on the length of the IP packet, and here we are matching packets between 10 and 100 bytes. It's also worth noting that if you don't specify a match command, the route map will apply to all traffic, which I do not recommend. Next we need to specify the action taken for packets that have been matched in the criteria. We could set the next hop value, we could set a QoS marking, we could set the default next hop for destinations not in the routing table. We could even do multi-VRF selection using the set VRF command, but typically that's used by service providers. You can also combine set commands together where it makes sense, such as setting both the next hop value and the IP precedence in the same permit sequence. And lastly, we then apply the route map to the incoming interface where we want policy routing to occur. Of course, we can also apply it globally as discussed previously. Okay, to get to the documentation from the main Cisco site, you go to Support and Downloads, Network Software, pick your particular version, but I'll do 15.4, Configuration Guides, and then it's actually under its own section in IP Routing, which is the Protocol Independent Configuration Guide. As you can see, there are many documents on PBR for the various features, but the one I recommend starting with is this one here, and that essentially goes over everything we've been discussing. Okay, so now we'll go into the demonstration. Okay, so here's the topology in question. We've got 5 routers, all running OSPF, and all of the addressing has been already configured. The loopbacks are 192.168.0.x, x being the number of the router. The only loopbacks we really care about in this demo are R1 and R5. What we actually want to do is make sure that all of the OSPF traffic is routing out of gig 02 on R2, and then when we source traffic from R1's loopback destined to R5's loopback, we want to send that traffic via gig 03 via R4. So let's have a look on R1, make sure we've got connectivity. And we want to make sure we've got connectivity when we source the traffic from R1's loopback, which we do. Now, at the moment, it's already going via R4. As we can see, R4's gig 01 interface is the .14. But that's with all this being equal, I assume that router 2 is just doing equal cost multipathing. So let's just quickly look at the routing table to see. In fact, we'll see the R5's loopback to see how it's reading the traffic. So as we can see, it is doing ECMP, and it just so happens that when we routed the packet, it chose R4, but it could just as easily chose R3. So what we need to do is manipulate the OSPF cost to make sure that router 2 is always routing via router 3. So let's go to gig 03 and give it a high value. So then when we look at the routing table again, as we can see, it no longer has the ECMP, it's going via router 3 because of that high cost that we just put on. So let's just test again from router 1, and yeah, it's different, it's going via router 3. So what we want to do is now do policy-based. Well, first of all, we'll try it without sourcing it from the loopback, and we should see that also goes via router 3. And then when we've configured PBR, that second, when we just do this without sourcing it from the loopback, we should see that goes via router 3, but the traffic sourced from router 1's loopback should go via router 4. So let's configure. Now I like to configure the access list first, purely because you're obviously trying to match that. You know that you're going to be using an access list in this particular case, so it makes sense to create it first and then do the route map. So let's just match the traffic. Basically permitting anything from router 1's loopback to destined to router 5's loopback, and then we'll do the route map. We will match the name of the access list, and then we want to set the next hop value. You could just as easily set the outgoing interface, but I try and I always do the next hop IP address, because on a multi-point broadcast interface you can run into issues with layer 2 resolution. So the next hop is .14. And now what we want to do is apply that on the inbound interface of gig 01. We should be good to go. Now I want to also run a debug command so you can also see what's actually happening behind the scenes. It would help if I was in exec. Okay, so let's do the same test. So first of all, we will test without sourcing it from the loopback. We expect this to go via router 3, which it has, and then we will source it. In fact, before we do that, we'll just look at the debug on router 2, and as you can see, that traffic was rejected because it hit the implicit deny at the end of the route map, and it just basically said that nothing was matched. So normal forwarding will resume based on the global routing table. So now we'll do it sourcing it from the loopback, and as you can see, it went via R4, and if we look at the debug, you can see that that it did say that there was a match, and it also said that it was policy routed. Now you can also look at the route map itself to see if you've had any hits. You can see that 9 packets had been hit, and the access list as well also had 9 matches. So pretty basic demonstration of PBR, but I hope it was helpful. Recommend trying it out for yourself and seeing what you can solve with it, because it can be a very useful feature to have in your tool set. So as always guys, thanks for watching. Please like and subscribe, and I'll see you in the next one.